What specific problem does your proposed method aim to solve in the context of LLM evaluation, and how does this differ from traditional methodologies?
The proposed method aims to address the significant challenges associated with the reliance on human annotated preference data for training evaluators in large language models, LLMs. Traditional methodologies depend heavily on costly and time-consuming human annotations, which can become outdated as models improve, limiting scalability to new tasks and evaluation criteria. In contrast, our approach utilizes an iterative self-training method that generates synthetic preference pairs without any human input, allowing for continuous model improvement and adaptation. By employing the LLM as a judge framework, we create contrasting responses and use the model's own judgments to label these pairs, resulting in a more efficient and scalable evaluation process. This method not only enhances the accuracy of the evaluator, but also matches or surpasses the performance of traditional reward models that rely on human annotations, as evidenced by our results on RewardBench.
Can you explain step by step how your proposed self-taught evaluator algorithm works? Include details about prompting, synthetic preference pair generation, and iterative model training.
The self-taught evaluator algorithm operates through a systematic iterative process. First, it begins with a large pool of human-written user instructions, from which a balanced set of challenging instructions is selected using an LLM for categorization. Next, for each instruction, the algorithm generates synthetic preference pairs by prompting an instruction following LLM to create a high-quality response, winning response, and a noisy version of the instruction to elicit a lower-quality response, losing response. This results in a synthetic preference pair, labeled as superior or inferior based on the responses generated. In the iterative training phase, the model, initialized from a seed LLM, generates judgments for these preference pairs by sampling multiple evaluations from the current model. Correct judgments are retained to construct a training set, which is then used to fine-tune the model for the next iteration. This process continues, allowing the model to improve its performance iteratively by refining its ability to evaluate responses based on the synthetic data generated, ultimately leading to enhanced accuracy in preference evaluation.
Please provide a simple example illustrating the inner workings of your synthetic data generation process for preference pairs. How do you ensure that one response is inferior to the other?
To generate synthetic preference pairs, we start with a user instruction, x_i, and create two responses, a winning response, y_i_w, and a losing response, y_i_l. First, we prompt an instruction following LLM to generate a high-quality baseline response, y_i_w, for the original instruction. Next, we modify the original instruction using a prompt to create a noisy version, x_i, which is still relevant but not semantically identical. We then prompt the LLM again to generate a response, y_i_l, to this modified instruction, ensuring it is of lower quality than y_i_w. This process guarantees that the constructed preference pair, y_i_w, suck y_i_l, is valid as the design of the noisy instruction aims to elicit a poorer response.
What are the practical benefits of using your proposed self-taught evaluator compared to traditional reward models? Specifically, address aspects like scalability, cost, and evaluation accuracy.
The proposed self-taught evaluator offers significant practical benefits over traditional reward models, particularly in scalability, cost, and evaluation accuracy. Unlike traditional models that rely heavily on large amounts of human annotated preference data, which is costly and time-consuming to collect, our method utilizes synthetic data generated through an iterative self-training approach, allowing for rapid scaling to new tasks without the need for expert annotations. In terms of cost, this approach reduces the dependency on human evaluators, making it more efficient and less resource-intensive. Evaluation accuracy is also enhanced. our experiments demonstrate that the self-taught evaluator achieves an accuracy of 88.3 on reward bench, surpassing the performance of traditional models that utilize human annotations, which only reached 85.6. Overall, the self-taught evaluator not only matches but often outperforms traditional methods while being more scalable and cost-effective.
Could you elaborate on the validation process you used to test the effectiveness of your method? What datasets, benchmarks, and metrics did you rely on to demonstrate the performance of your self-taught evaluator?
To validate the effectiveness of our self-taught evaluator, we utilized several benchmarks, including Reward Bench, MT Bench, and HelpSteer 2. The evaluation on Reward Bench followed the standard protocol provided by the leaderboard, where our model achieved an overall score of 88.3 after 5 iterations, significantly improving from the initial score of 75.4. In MT Bench, we reported agreement rates with human judgments, focusing on non-tie examples, and found that our model outperformed the Llama 3-70B Instruct seed model and performed comparably to GPT-4o125. For HelpSteer 2, we assessed average accuracy and position-consistent accuracy, demonstrating improvements over the seed model. Overall, these evaluations highlighted the superior performance of our self-taught evaluator compared to both the initial model and existing reward models trained with human annotations.
What limitations or drawbacks did you identify in your proposed method, particularly concerning its applicability or computational cost, and how might these impact its real-world implementation?
The proposed method of using a generative LLM as a judge has notable limitations, particularly regarding its computational cost and output length. Generative models typically produce longer outputs, which can lead to higher inference costs, making them less efficient for real-time applications. Additionally, the study primarily focused on evaluating the accuracy of pairwise comparisons, leaving the evaluation of single responses for future work, which limits its immediate applicability in scenarios requiring single response assessments. These factors could hinder the method's scalability and practicality in real-world implementations, especially in environments where rapid evaluations are necessary. Overall, while the method shows promise, its computational demands and restricted evaluation scope may pose challenges in broader applications.